Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Integrating Growth and Decay Models. Please be an active learner as you watch this video. These are the learning objectives you're supposed to accomplish, and so at the end of this video you should be able to check back and make sure that you can do all of these things, because the questions on an assessment in the future might very well have you doing these things. By way of introduction, previously in sections 2.3 and 2.4 and 2.5 rather, in your textbook, we studied exponential growth and decay models. We found that the growth model was P of t is equal to P0, the initial amount, times e to the kt. Here k is bigger than 0. And the decay model was P of t is equal to P0, the amount you had at the beginning of the period, times e to the minus kt. And again, k is bigger than 0. So this was decay, this was growth. In this section, we consider applications of these integrals. And for convenience, we first derive formulas for evaluating these integrals, and then we'll talk about applications of those. So recall that in a financial problem, the interest rate k is expressed in decimal notation. And so what we would find is, for the growth model, a formula that we would have for the integral from 0 to t, and this is like continuous compounding, for example, P0 e to the kt dt is going to be, the P0 can be pulled outside the integral, you're integrating e to the kt. We're going to use substitution, you let u equal kt, and what you should get for your indefinite integral is P0 over k times e to the kt. Make sure you understand all of these steps. This was a substitution that we used. We evaluated the top value minus the bottom value. That's the fundamental theorem of calculus. So when we put t in there, we get this. And when we put 0 in here, we get this. But this is 1, and so this is the formula that we will get for the integral from 0 to some time capital T of that exponential growth. So that's sort of an accumulation of the exponential growth. So here's the formula for that. Is P0 over k, e to the kt minus 1. Now similarly, for the decay model, if we were to do the same thing, we get this. The signs are different, and you should check this calculation. But the integral from 0 to, that should be a capital T there, of P0 e to the minus kt dt is equal to, and we get the capital T there, so this is P0 over k, and this is 1 minus e to the minus k times capital T. So we're going to use those formulas. So the two formulas you should remember is that this integral is equal to this, and this integral is equal to this. And again, that was a capital T, not a lowercase t. The first topic we're going to talk about then is future value. And we've talked about this before too. So the basic model for growth of an amount of money presented in the following definition. So P0 is invested for t years at an interest rate of k, compounded continuously. That's how come you get the exponential rather than just a discrete formula. Then P of t is equal to P0 e to the kt. And P at 0 is the amount we had at time 0. And this value, P of t here, is called the future value for P0 dollars invested at rate k, compounded continuously for t years. So here's example 1. We're to evaluate this formula for the P0 is going to be 36,500. The time is 4 years, and the interest rate is 3% compounded continuously. So we're going to use this formula, and we will substitute those numbers in. We do the calculation, and what we will get is this as an answer. This is approximately equal to, because we're rounding it off. Now, using a calculator, and you should realize that the calculator that you're going to be allowed to use is going to be the calculator on your screen, and so make sure you know how to do this. And I went through and actually did the calculation over here, and you see this is what I got for the answer here, and they rounded it off to 6.4. Let's look at another example. Now this is the accumulated future value of a continuous income stream. Okay, so in this example, the owner of a parking space near a convention center receives a yearly profit of $36,500 at the end of each of 4 years. Now this is the income stream, so he gets this every year. But he really should have that money working for him, so he invests this at 3% interest compounded continuously. So every time he gets this, this income, he invests it there. And so what happens is, at the end of year 1, this is what he got, but then he's doing that for 3 additional years, and so that becomes this number. And the second year he gets this again, but this is going to be sitting in his interest-bearing account for 2 years, so it's going to be this number. Here is what he gets in the 3rd year, and in the 4th year he really doesn't have an opportunity to gain any interest on that at all, because he just gets it at the end. But he's certainly gaining a lot of interest here, and so the future value, the total future value of this income stream, given his investment, is this. Now you could say, well, okay, that's good, but he could probably invest this in something that gave more rapid return, and the answer is we'll see that that's true. So next, suppose the owner receives profit of $36,500 per year, but in payments of but in 365 payments of $100 per day. So he's getting this money more quickly. We're working towards getting it continuously. So each day the owner gets $100 and he invests it at 3%, and this is compounded continuously. Now what happens here though is you can here we're doing it every day though, and so what happens is you are doing, instead of this, you're taking this divided by this 365, that's $100 a day, and you're investing it. But now what you're going to get for those is going to be this amount, because what is happening is you're getting daily compounding and so on and so forth. And so if we're doing daily compounding over 4 years, we would do this 1,460 times. We would be adding these up. Now you see this is starting to look more and more like a Riemann sum. And in fact, if you think about what this is going to be, and you rewrite this in a way that looks like a Riemann sum, you're getting closer and closer to having an integral here instead of a long-standing sum. And that's exactly what happens in the limit. And so this is the definition. So the definition of an accumulated future value of a continuous income stream is, if we let R of t represent the rate per year of a continuous income stream, and we let k be the interest rate, but it is compounded continuously, not every day or every hour, but continuously, at which the continuous income stream is invested, and let capital T be the number of years for which it is vested, then the accumulated future value of this continuous income stream is given by the amount is equal to the definite integral from 0 to capital T, R of t, e to the k, t minus t, that's capital T minus lowercase t, and we're integrating d lowercase t. Now it turns out, since we're integrating with that, this e to the k capital T is a constant. I can pull it outside, and then I'm evaluating this integral. Now if R of t is a constant, it too can be factored out, and we will have this as an equation. So if we factor out the R of t, I have e kt, and then I also have R of t factored out, and then I'm evaluating just the integral of e to the minus kt dt, which is this. Now if R of t is not constant, then this equation 5 does not apply, and the integral 4, that's this integral, has to be evaluated. So if R is not a constant, it's a function of t, you'll multiply this together and do the integration. Let's look then at an example. Now this is an example, I think, where it is constant, but we will see. So this is called insurance settlement. So a cardiac surgeon, Sarah, who earns $450,000 a year, is involved in an automobile accident that prevents her from working. In a legal settlement with an insurance company, Sarah is granted a continuous income stream of almost $250,000 per year over 20 years. Now, each year she can take this and invest this money at 3.2% interest, compounded continuous in the HALMOS. HALMOS is a famous mathematician. Global Equities Fund. Find the accumulated future value of this continuous interest stream. Now here, R of t is a constant because it's this number, so we're really just using this formula 5, and we plug in the numbers. I encourage all students to plug these numbers in to make sure you can do this with your calculator, and not your calculator, but the calculator that's on your PC, because that's the one that you're going to be using during an assessment. And so we plug all of those numbers in, and we see that this is approximately, rounding to the nearest dollar, of what her accumulation will be. Okay, so we're rounding to the nearest dollar. So it's a little bit over $6 million. Actually, quite a bit over $6 million. We can also talk about the concept of present value. Now, in example 1, we talked about that the future value of this invested for 4 years at a continuous compounded interest rate of 3% was this number. That goes all the way back to the first example we did during this lecture. Now, this initial amount is called the present value of that, when of this figure invested for 4 years at an interest rate of 3%, compounded continuously. You see, this answers the question, what do we have to invest now at a certain fixed interest rate to attain a certain future value? So you see somebody saying, I want this much money to buy a house. How much do I have to put down into an instrument like this that will get me there? Okay, well, to solve that, that's pretty easy to solve. In general, the present value P0 of an amount P that results from an investment at interest rate K for t years is found by solving the growth equation for P0. So here's the growth equation. P of t is P0 e to the kt. So we solve for P0 and we divide by this, and that's the same thing as writing P e to the minus kt. And so that is the definition of the present value. So the present value P0 of an amount P due t years later at an interest rate K compounded continuously is given by P0 is equal to P e to the minus kt. So you see, to get this future value, how much do you have to invest in one lump sum? Let's look at an example of doing that. So here, this is called example 3, we have in 10 years, Sam is going to receive a $250,000 under the terms of a trust established by his aunt. Now, if the money in the trust fund is invested at 3.25% interest, compounded continuously, what is the present value of his trust? Well, you see, the final value is $250,000, and this is the formula, this one. And so we get that the present value is approximately $180,631.84. That means if somebody were trying to buy this from Sam, that would be the fair price for them to pay. Let's move to another topic. Now we're going to talk about the accumulated present value of a continuous income stream. And so we are going to work backwards from the equation that we had earlier, and this was the one for the amount of this continuous income stream. So now we're looking for the principal amount. You see, we want the present value, so we're looking for the principal, the one-time deposit, at which at the interest rate K, that will yield the same amount as this. So we're going to set this equal to capital B e to the kt. So we're solving for capital B. So we divide both sides by e to the kt, and we get B is equal to this. And this can be simplified by by observing we have a common denominator. And so when we do that common denominator, we're going to have, and we can simplify it to get 1 minus e to the minus kt. You should really check and make sure you understand the algebra going from here to here. So this is the expression for B, and that forms our definition. Okay, so this is the definition for accumulated present value of a continuous income stream. So let R of t represent the rate per year of a continuous income stream. We let K be the interest rate compounded continuously at which the continuous income stream is invested, and let T be the number of years over which the income stream is received. And that this T is a capital T. Okay, so if R of t is a constant, and then B, the accumulated present value of the continuous income stream is given by this. Now this equation 6 is exactly what we solved for up here, so that's just restating what we talked through up here. If it's not constant, you're going to have to integrate it, and so we're going to integrate from 0 to capital T, this R of t, e to the minus kt dt. So let's do an example here of that concept. Here we're determining the value of a franchise, and the franchise is called Silver Spoon. So Silver Spoon operates frozen yogurt franchises. Chris is considering buying a franchise in his hometown, Carmel, Indiana. There actually is a Carmel, Indiana. As part of his decision to purchase this, he wants to determine the accumulated present value of the income stream over an 8-year period. He's expecting to be breaking even, and that means this is a fair value for him to pay. Now the Silver Spoon Cafe franchise tells Chris that he should expect a constant annual income stream given by R1 of t is equal to $275,000, which Chris knows that he can invest this income stream at 3.3% compounded continuously. So that is cash stream 1. However, Chris performs a linear regression on the data from the annual reports of Silver Spoon, and this really should be based on the geography and the demographics in Carmel, which indicates that there will be a non-constant annual income stream of this. R2 of t is 80,000 times t. So you see this is a different income stream, but it's what he thinks he can get. So it has these two things to evaluate, and that's what the problem is going to be focusing on. So part A, we're going to evaluate the accumulated future value using R1. That's what the Silver Spoon franchising organization says he can get. So we're going to evaluate the accumulated future value and then evaluate the accumulated present value of that income stream and interpret the results. Now this is kind of complicated, so do think through what's really going on here. So let's do part A. So you see this is a fixed amount, is $275,000. So it's going to be that equation that we developed in the previous slide. And so it's going to be this equation. We plug in all of the numbers and do this. Now again, students should calculate this. It's going to get a little better than a little better than $2.5 million is his expected value that he would get there. And so this is what the Silver Spoon franchising people would perhaps be talking about relative to this revenue stream. So this gives Chris a sense of what is the value of the franchise going to be over the 8-year period. But now we're going to talk about the future, the accumulated present value is found by using an equation that we called 6. And so it's going to be, we're substituting in here, and we get this is what Chris should be thinking about paying for this now to break even in that period of time. Okay, so anyway, so the first result tells us that, and this is what B is going to be. Now, the first result tells us that if Chris were to buy the franchise now and invest it continuously, he'd have a little bit over $2.5 million in an 8-year period. The second result tells us that that is worth almost $2 million today, and so that would be a fair asking price. But now Chris wants to talk about a different scenario, and so now he's going to evaluate the accumulated future value of the income stream at R2 of t. And then he's going to evaluate the accumulated present value of this and interpret the results. Okay, so what we're going to do is with a non-constant income stream, R2 of t is 80,000 t. So we're going to substitute 80,000 t into this equation. So there's the 80,000 T. And again, this can factor out because it's a constant. And then the 80,000 can factor out, but then we have this. Now, everybody should realize that this is going to involve integration by parts. So you want to do this very carefully. You're going to let U equal T, and dV is going to be everything else. Make sure you can do these calculations. We studied this previously. So here you're going to do integration by parts, as I said. And then the integration by parts, actually, you do this, and then you do this. You evaluate it at the endpoints and do a lot of the calculation, and so this is what you will get for this number. Now this result, and this is a little bit over 2.8 million. This result tells us that if Chris were to buy the franchise now and invest the predicted income at 3.3 compounded continuously, he would have an income of this. So you see, they're being a little bit maybe pessimistic on this. And so now what he will do is he will have 2.8. And so the accumulated present value then is this. And again, we're integrating this value. And again, it's integration by parts to get this. This tells us that the $2.8 million is worth about a little less than 2.2 million. These computations yield a higher accumulated present value than claimed by Silver Spoon, suggesting that Chris is dealing with a reputable company, and in fact they're offering him a good deal. Here's another example, but we're addressing a different application, but a similar kind of concepts based on what we've studied. So Emma and Jake want to establish a college trust fund for their new grandchild, Erica. And they want to have $100,000 in this account by her 18th birthday. So you see, that's the goal. So the question then is, what lump sum do they have to deposit now at 3.5% interest compounded continuously that will yield the $100,000 when Erica turns 18? Okay, well, that's going to be P0 is equal to, this is the equation that we have, and we find that if they deposit a lump sum of $53,259.18, they'll get there. You should make sure that you can plug this into your calculator. Now, they discover that the required sum is more than they can afford at the time, so they decide to introduce and invest a constant income stream of R dollars per year. So now what they're doing is they're putting money in continuously rather than a lump sum, because they don't have the $53,000 to make that happen. So what we're going to do is we need to find R of T such that the accumulated future value of the continuous money stream is $100,000, assuming the interest rate is still as it was and still compounded continuously. So we want R of T such that we have $100,000 at the end, and this is our equation. So we solve for R of T, and R of T, it's the only thing that we don't have a number for. So we'll get R of T is equal to approximately a little less than $4,000. So you see, they can put in money at $4,000 per year, and it will be invested in compounded that will yield the future value of $100,000. And they can probably afford this more easily than they can the $53,000 as one lump sum. Let's look at another example of this. And this is about buying out a contract. So suppose Gregory is playing basketball under a contract that pays him $3 million per year, each year for 5 years. After 2 years, the team offers him a buyout of his contract. How much should the team offer him? And assume an annual percentage rate of 2.8 compounded continuously. So you see, when they're doing this, they're factoring in the fact that that there is an investment opportunity that will give them this compounded continuously. So we're going to view this this 3 million as a continuous money stream. Okay, so after 2 years, it's going to be this from the formulas that we had before. There's the 2.8. So that is the accumulated future value. Now, if the contract were allowed to run the full 5 years, the accumulated value would be this. So the difference is this amount. Now, again, make sure that you can follow these calculations. So since the team is offering a lump sum payment to buy out the contract, Gregory should expect that it would allow him to invest it somewhere else at 2.8, compound continuously for the remaining 3 years. That would yield that amount or more. That is, he should receive the present value difference of this. This is our present value formula. So this is P0 is equal to the amount, the difference over the 3 years, and then we discount it by the factor e to the minus 0.028 for 3, and we get this. So that's the present value. Now notice that this is less than that because he's going to be able to invest it this way. And this is the kind of calculations that baseball teams do. And that was a basketball team, I guess. Now let's look at another example. I think this might be our final example. We're going to apply these concepts to the life and physical science. We're going to talk about consumption of natural resources. Okay, so this is, again, we're going to be integrating the kinds of growth functions that we're talking about. And this is as a model of the demand for natural resources. Suppose that P0 represents the annual amount of a natural resource, such as natural gas or oil, to be used at time 0, and the growth rate for this resource is K. Then, assuming exponential growth in demand, the amount used annually T years from now is P of T, which is this. So the total amount used during an interval 0 to capital T, that's a fixed number, then is given by, it's the accumulation of that. So we're going to be integrating that. P0 can be pulled out. We've done this integral before, and that's an equation that we had from before. So now let's do a real example of that. And this just is a restatement of that exact same formula. Okay, so let's look at, and I guess we really have 2 examples. The first one is going to be gold mining. In 2016, the world production of gold was 3,100 metric tons, but it was growing exponentially at a rate of 3.2% per year. And apparently these are real numbers from some government finding. If the growth continues at this rate, how many tons will be produced from 2016 to 2024? Well, the way we're doing our scale here, 2016 was t equals 0, so we're going to be integrating from 0 to 8. This, and it's exponential growth, that way, continuous compounding. And so we get this. And you should check to make sure, but if you plug this into your calculator, you're going to end up with this is going to be a little over 28,000 metric tons of gold will be produced during that 8-year time period. Here's another example. This one is dealing with the depletion of gold reserves. The world reserves of gold in 2016 were estimated to be 56,000 metric tons. Again, that's from perhaps the same report. Assuming that the growth rate of, this is the same growth rate we had before, 3.2% per year continues, and that no new reserves are discovered, when will the world reserves of gold be depleted? And this is an important kind of question for planners to know about. So then we want to find T, capital T, and it's sitting right here, such that this is true. So we're going to solve for capital T. So we do this calculation, 3,100 divided by this to get this. Then we divide both sides by 96,875 to get this. We add 1 to get this, and then we're going to take the natural logarithms because the t is up here. So we're taking the natural logarithms. And that means that we're going to have the natural logarithm of e to the something is just the something, it's just the exponent, and this is the natural log of this number, and then what we can do is divide both sides by the coefficient of t, and we get t is approximately equal to, we're rounding it off, but this is 14.26 years. Now that means that if the production of gold continues to increase at that and no reserves are found, that the world reserves of gold will be depleted 14.26 years from 2016 or sometime during the year 2030. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.